hyperspectral data. Any kind of the remote sensing data is there, you can do the change analysis, right, as per the application, as per requirement, right. So these are the contents, but most of the things here is already covered in my previous lecture. So some of the content we will skip that. These things as a very requirement, as a prerequisite, but these things already discussed previous class. Yeah. Here we'll start from this. So as you can see the slides, so first question is what is change detection in remote sensing, right? And then change detection is nothing, it's kind of the method or technique for finding the difference in the shape of an object or the phenomena by observing it at a different time instant known as a change detection, right? Standard definitions. So in simple word, so if you wanted to find the change analysis, right, of a particular geographical locations, so we need to have two remote sensing data which are captured at a different time instant, T1 and T2, right? And this time difference should be minimum 3 years, right? Or 3 years, 5 years, 10 years, 7 years, depend on the availability of data. If you take a smaller durations, you may not find the availability of the data or may not find the, the changes, what has happened that, right? Normally, as I told you yesterday, the changes which you see in Indian context, like at least any project is started, it will be take 2 to 3 years to complete, right? Like a building or any complex constructions, right? 2 to 3 years is normal project durations, right? So you will see that the difference of the buildings or maybe the road or the some rail networks, right? Which you can see that a new rail network is, that created, right, by the Indian Railway government, right? So, but rail network will not have rapid changes, like only the some part of India you may say that now some new rail network is started, right? So very rarely you will find that the changes in the rail network. So as far as the type of the change detection is concerned, so we have two kind of the change detections which we call as a first binary change detection, which short form we call as BCD. As I told you in my study class also, binary change detection is a simplest task, right, but very useful, right. So it will just kind of the changes, like changes, no changes, you will find that. But what kind of changes there, if we are also interested to know, then we need to go for the semantic change analysis, right. So semantic change detection is a method which will tell you what kind of specific change happen, like whether like like forestry change to the agriculture or agriculture change to forest, right, like the vegetation change to the like other objects, right. So how the vegetation is changing from one class to the other class, right. That kind of change analysis if we are looking that, in that case you need to go for the semantic change detection, the concept, right, SCD. SCD is little bit complex, right, because it also uses the concept of the BCD sum, right. So straightforward you cannot do the semantic change analysis. First you need to understand that binary change detection, and binary change detections you will come to know is nothing that whatever the model we discussed yesterday, right, semantic segmentation model, those models you can use for the change detection analysis. So it's a linkage is there, right, like the segmentation model you can that use for the change detection analysis, right. So this is the simplest example you see here. This example state that we have called T1 image and the T2 images, and then this is a change detection method. It could be any method. It may be a non-deep learning methods, it may be a deep learning methods, and then finally you see that the change map. So change map which you can see over here is there are black and white image, right. So black and white region represent the change from that T1 image to T2 image, right, and the background that is called no change area, right. So white region, white color represent the changes, black represent that no changes in the your landscape. Okay. So here you see that unchanged, already mentioned, right, as a legend. Then moving ahead, the example of the semantic change detection. So here you see that we have to again require the two images, T1 and T2, and then semantic change detection methods. So it will give you the two map, right, semantic map, right, for this is called semantic change map 1 and this is semantic map 2 here, right. So if you see that for the same case, you can find that what the things are changes. For example, see here, this is T1 image, T2 of the same places. So here this color, all the like no change, white is no change, building and the ground, the tree and the low vegetation, water and playground, right. So each cases you can see, and then you can see that what are the changes happen, right now, what is specific changes happen from T1 to T2, right. So all specific changes can be seen by looking both the change map, like this nothing, this is thematic map, right, which also you can call like land cover mapping, which already we have seen that. Okay. So this is very important task to come to know what kind of changes happen from T1 to T2 image, right. And then this example you can see very clearly, like from the same data and the both the differences, like binary change detection and then semantic change detection here, right. So this you see very clearly. So you have only black and white image. So white region, as I told you, is change, and then black is no change area, right. So area change only you can see that. Here if you see that same case, so you can see that like what kind of specific changes happening, right, now from the T1 image to T2 image, right. So all those analysis you can extract from the that SCD methods, right, applying that. Then coming to the data, so again data comes from the surveillance camera based or maybe drone, aerial, multispectral, hyperspectral and SAR data. So change analysis is possible from here to here, like surveillance camera leave it, right, will not happen, but drone, aerial, multispectral, hyperspectral and all. So change detection analysis you can apply for any sensor data, right, aerial, drone, multispectral, hyperspectral data. But of course, right, you require the data, and the data of the, you should have some public data or you have to capture by flying the drone, right. But if you are flying the drone, so you should have a data of 5 years back for the same locations. That time you may not have the drone, but if you want to do some work analysis, so you capture the data in today and you capture the data some specific city after 5 years, right now. Then it will possible from your drone base, right. Instead of that, you better go for satellite data. Satellite already have the data in there, that cloud will be there, right, server, right. So you need not to do that, right, yourself only, better go for the multispectral data which already available in the server there. You just download that, request it, right, they will give you the data of which year you want data, right, which time you want it, right, that part you can get it from that. These things already I have discussed you. So again, once you say that change analysis, right, so binary BCD, it's come under the regression binary classification task, right, as a pixel base, right, whereas your semantic change analysis will be on the as a multi-class classification research task, right, now, because that will be employed both, right, like your that uses the this as well this here, right, because we'll be using the for the semantic loss function, that softmax loss function, and also binary task. Okay. So here, it's already seen that. So now, before moving to deep learning algorithm, so first important, available data. If available is the data is available publicly, at least you get some confidence. Yes, data is available. I can develop a good deep learning models for the task here, right now. So once little you mature, then next your the task could be create a data set for Indian context, right? Indian geographical regions, right? So that at least our Indian, remote sensing that the researchers, they can use, they can learn, and they can have some more new things, right? Normally, if you say that in the context of this remote sensing data, most of the data comes from the Chinas. They are the creating a lot of things. So they are creating, and that's why their publication will be also large. I mean, publishing quickly, and their citation is very high, right? Because if you create data, your one advantage is you will be recognized globally, right? Because this data set coming from this particular university, this professor team created, and then the paper which you publish will be cited by everybody. So as the institutions will get advantage, I mean more recognitions, as an individual, your visibility will be more, right? So have multiple advantages, right? And also our Indian, like we try to help the Indian, researchers so that they can also think about creating the way you have created that, right? So this is a first data, right? So the data set which we call labor CD. So this labor is nothing, learning, vision, and remote sensing. This is the this professor Sai, so Chinese fellow. He is actually his lab. This is in lab, his lab name, right? Right. The data, what the name he has given is his lab name, right? And then CD means change data. Very simple. Likewise, we have also created a call NK computer vision deep learning data set, right? So our lab is also coming to the picture in the very soon, right? The data set which we are creating, be from our lab name, then whatever the data is like building, road, change direction analysis, and so on, right? So this data set, if you see over here, so called T1, image 1, image 2, and the ground truth you can see here, right? And this data, what he has captured mainly from the 637 Google Earth images of the patches which created with the high resolution of 0.5 meter per pixel, and patch size of 1024 cross 1024. Training set is 445 patches pair, validation 64. This patches he has created from the data set whatever is available, and test samples have 128 patches, right? So this is all, I mean that established in 2020 by the same lab. This is a link available, you can download that. The Chen H and Z Sai. So this is a professor, right? And this is a research scholar. Both they have created this data set, right? And span of, look at the data right here, 5 to 14 years. It's just a bearing span of the data, right? From their city, China only, right? So this data set is frequently used, right? And this is not very complex data, right? So here you see that the data is Google high resolution, so it's very good data set, right? Moving ahead, this data set is called as a OCD data set, right? Onera satellite change detection data set. This data set is created from the Sentinel-2 sensor from European agency and covering the 24 region worldwide, right? This is more good data set because this data set having the RGB images also, and this data set is also having the multispectral bands also. And Sentinel, as you know, right, Professor Fabio, right, comes from the Europe only. So, right, that's called Sentinel is having the 13 bands sensors, right? So you can work on all 13 bands, right, and you can work only on the 3 bands as well, right, depending again on your computing facility, whatever you have, right. So this data set, in fact, in this 24 regions of worldwide, so in India, they have also captured from the Mumbai regions, right. So Mumbai is that region from where the data is also available, like Mumbai, Abu Dhabi, and like Dubai, right? So every most of the country they have considered while creating the data sets, and this is very good data set, I would say. If your algorithms works very good on this data set, right, that will work on further less complex data set. So complexity involvement is more here because variability is more here because it's covering that land dynamics of the various countries, right? So everywhere the urban the dynamics will be different, right? So focusing only on the urban growth and the changes. That's Mumbai is that is the capital of Maharashtra. Here that very dynamic changes happen over there, right? And then resolution is between 10 to 60 meters. So resolutions will be here 10 to 16 meters, right? And the bands, as I told you, 13 bands, right? And then patch size is 512 cross 512. And the training patches are 200 and validation for 57 and test 30 patches. This is the data kit by the .rc in 2018, right? And this data set is available from this IEEE data. Yes. So this is again the IEEE data port, right? Is from where you can get very good data set, right? Validated data set, right? From the IT data ports. And we have also worked on this. So we have worked on the RGB images also, and we have also worked on the complete paper, which already I have shown you called UCDNet model, right? Which we designed that. That's on multispectral bands as well. And then other is called WHU building data set. So basically Wuhan, that area of that China. And they have also have different like 2011 to 16. I mean the different time span and the size of, see here, 15,354, right? That image, whatever they capture that, right now, 15,000s. So, and cross 32,507 pixels. So you can understand that what the geographical regions they have covered in this image, right? Now capturing that. And this is what the area, New Zealand, they have considered that. But this, because the lab is created from this Wuhan, right? So they have name is game, but the study area they consider that this is in China and this is in New Zealand as well. So spatial resolution is here 0.2 meter, right? And patch size, after this is a like complete image, big satellite data, right? From that, they are using creating the patches of 512 cross 512, because most of the deep learning, right, accept the patch size is 512, or you can go even the 256 cross 256 right now. Why this? Because computing is a problem, no? If you give that, the computing won't happen, right? So smaller patches, right, with the batch size of, like one is other important batch size. So batch size should be the power of 2 while training the model. So the power of 2. So it may be batch size 2, right? It may be batch size 1. If you use batch size 1, that may work, again depending on the computing, 2, 4, 6, right? 16 like that, right? So batch size, you can have more sample patches, you just give it to the batch of the samples, right, at a time while training the model. And so this data set what created is again use, but only that that's only building objects. They focus only the infrastructure, right? So building infrastructure only you see the changes over here, right? Whereas previous is multiple changes you can see that, right? That's why this is a complex data set, right? So not only building, even classes also is you can see in the data set whatever they have created. From my point of view, this is the good data set and they have put a lot of efforts while creating that. Okay. Creating single object data set is a very simple task, right? It won't take much time. But when there is a multiple changes you need to highlight, it is basically complex, takes time, a lot of time creating the data set. And this is data sets comes in 2000, this recently data set, it's last year, I think last year. And this called Sun Yat Sen University CD data set. So you see the data set, either the university name creating or the lab name they are creating right now. And here also, this data set again is not very complex data set, right, if you see here. So covering the Hong Kong in the south of China, images between the 2007 and 14, that means 7-year gap, right, they have taken. And total of 200 pairs of the images, spatial resolution is 0.5 meter per pixel, type of changes, newly built urban buildings, suburban dilations, groundwork before construction, change of vegetation, road expansion, sea construction, and so on. So patch size, what they created is 256 cross 256, right? Okay, so this data set, the patch size is a 256 cross 256. So in a different data set, you will see that the patch size is different. But standard, mostly you find what? 256 or 5112 cross 5112. These two are the frequently used patches size. If you're creating new data set, you can create 256 cross 256 or 5112 cross 5112 right now. This is again data set which coming from the China only, right? Okay, so that's why I told no, we should be create something, right, from not only why China always, so our India should be also in the leading for creating the data set, right? With that passion, with that motivations, we started creating the data set, right? So this data set again from Google Earth Images, right, created that, and like covering the 6 cities, see here, Beijing, and this of the all China city only. Spatial resolution is here 2 meter per pixels. Okay, previous was even the high resolution, right, 0.2 meter, right, even the little lower, right, resolutions here, and taken time between 2001 to 19, right. So the gap, right, 2001 to 2019, that gap here, right. And patch size is again here 512 cross 512, right, clear. And then 3940 patch pair, and the test sample is 48 patch pairs, right. This is the link from where you can download that, okay, no problem, right, already there. Then that whatever previous you have seen, that was for BCD data sets, right, binary change detection data sets already available, right. We are also created the data set, but we will soon share that this year only from the Indian context, Indian geographical regions, Indian satellite sensor as well, right. So this data set is the first data set for semantic change detection analysis, right. The data set name is called second, right. So semantic change detection. So this data set was created in 2020 as a paper, you can see over here, and this is a link again comes from Wuhan, that WHO only, right. So university only, right, the data set, and consists of 2968 pair of 512 cross 512, right, images labeled by temporal aerial images of these 4 cities here, right, and consider 6 semantic types like playground, building, water, low vegetation, tree, and the no change and fake change, right, as seen, right. So this is what the data set, and you can see the as example over here from A to D, right. So T1 image, T2 images, T1 label and T2 label. So as I told you, right, we need to, if you want to create a new data set, you need to create a 2 on the ground truth, right. Data 1, T1 image, you have to create the map and the ground truth for T1 image, then you have to create the T2, whatever the image there corresponding the ground truth you have to create, right. So you think that how much time you need to spend right now. So that's why the guy who has created the data set always respect, because he has put lot of efforts, time, and then created the data set right now. It's not easy task. In general, to study one study area, right, like my student spent 1.5 months for creating one scene for the that land cover map, okay, and took a lot of time there. Though after the little experience right now, but it's still 1.5 to 2 months required for one study area creating the ground truth map. So all the things you can see that this is required, right, and this is a paper, right, you can refer that. This used in even the, again 2024. I refer took image from there, but it is created in the first was in this paper, right, okay, and this is again data set which is very less used, but here this is called Landsat SCD data set, and this data set consists of 2425 pair of here 412 cross 412 label, right, patches, and covering the regions 1990 to 20 here. So the here gap is 2 more high, right? They created the data set. 4 cementing type, farmland, desert, building, water, and no change. And in addition, the image scale of this are reshaped into a 512 cross 512, because this data, this size is no, but not there right now. So size also is evenly used, right? Right. Again, to the power of n, right? So it should be 256 or 512, no, 5 that's. And why the batch size should be power of 2? Because it linked to the GPU machines, right? So that if there, the computing will be better. That's what what the NVIDIA. One more suggestions I'll give you. Everyone, if you are passionate about this field, you need to go to also that account in the NVIDIA, right? You will get lot more, that the resources, learning, right? And free things, webinar, courses, you attend that, right? NVIDIA, right? And that NVIDIA, just Google it, you get that, which they are, manufacturer of this, your GPU, graphics card, and then boards, and then server, NVIDIA server, computing, all things there. So good to know, become the member of that, and that's called Deep Learning Academy Library, right? You can join that and you can do lot more tutorials, other things you can explore that library, right? So this data set, is here used in that 2022, and this is example you see again here T1, T2, and this corresponding that mask, right? Label 1, label 2, right? For 4 samples here, right? This part already, as we have already discussed, right? So coming to the algorithms for the urban land cover change detection analysis, or in general change detection analysis, right? So there are 2 methods used, that's called traditional algorithms, another we call as a deep learning methods, right? So traditional methods here are as follows: image algebra practices, statics based method, image transformer methods, classical methods, advanced algorithms, right? And still ISRO, whatever the data, I mean that use in your get it from the ISRO, that we will get actually the pan-sharpened data, right? So they still using the traditional method for doing the pan-sharpening method, like fusion actually concept, right? Now, we haven't not talked, but they're using. So, but still these methods, some of is okay to understand that as a not without deep learning. Few algorithms need to implement that from the non-deep learning, get idea, then you can switch to the deep learning methods, right? I'll not go deeper, right? Because these are, not used in the industry as of now. Everywhere going to be future only the deep learning based approaches, right? And then these are the deep learning methods. So in deep learning methods also, again, there are various types, which we have called feature based methods, patch based method, and image based methods right now. So you can use any one methods here. So I would recommend you can go for, and you see that here image based methods. So because here the segmentation concept can be used, right? Each cases different concept will be used, right? So when you know segmentation approaches, right, you can extend the same models, right, for the change detection analysis, right? It will be easy, right? Because you have understood now each and everything about the segmentation model. So it is easy to take it the next task as well, right? And even you can use feature based method or patch based method also you can use, right? With deep learning, where it will be called center pixel change analysis. Then why need deep learning methods for change detection from the bitemporal? Because program like this Copernicus, Landsat already have a massive volume of data available, right? So data is not a problem. Data is not a problem. Free data is also available, right? Like Sentinel-2, Landsats, right? These are available right now. And likewise other sensors also available. So you can available data already there, you just download. Your role is, right, either developing the deep learning algorithms or from the available sensors just create a data set right now, okay? and use it applied the existing algorithms. It's up to you, right? How much time you can devote for the research, right? If you more time devote, more outcomes will come, more visibility will be there, of course, right? And WordView, QuickBird, Deep Globe, right? These Sentinel, GF, our IRS, Cartoset, and other sensors, these are having the lot more data is available. Our data from our Indian satellite, India, that's this from IRS, right? ISRO is not very costly, 4,000 only per study area, right? 4 to 5,000, that's all. And you get high resolution images, right? Which you can use, you can build that, right? Likewise, other data also available, okay? So, two major problems with the traditional methods, like handcrafted feature extraction using, so which solution would be here automatic feature extraction, so that's why deep learning will be help us, and output is not meeting practical requirement, right? So that's why you can go for advanced deep learning algorithm method for the change detection analysis from the bitemporal remote sensing images, right? So see that this is a list of deep learning architecture for binary change detections right now. So you can start from here if you see, just see the list, right? Model. So that's called fully convolutional SIAM network concretion, DCIAM difference, which was introduced by the 2018. Who has introduced? This guy who has created the Onera change detection dataset, UC data, OSCD dataset, right? So he has started the first one. So first he has created dataset, he has used the model. So his name, his popularity, his citations will be huge, right? Now, because he is the guy who has first created the data set and first use the models, right? So his work always will be reference for others, right? So that's what kind of the work need to do. And then UNet++ model also used for 2019 by Peng et al. DSIFN 2020, AGC.NET 21, ADSNet 2021, then became it UC.NET, Green, our lab, right? So that's called 2020 by Basaraju et al., my student, and RSCDNet 23 by, again, my lab, right? And then ECFNet 2023 by other researcher, and then BC.NET from my lab again, we are there in called 2023 by again, this is scholar, and then SEIFNet 2025, this Hang et al. Again became a ERS CDNet in 2024, right? And then and so on, right? So you can also get some other models. So this is how it started from here, and in 2024 we are here, it was here right now. And also you can find the models. So current benchmark, you need to select that so that result you can do that part. Then for the semantic change analysis, so these are the, again, started from 2022 models here, right? So you can see the all models. So we have started last year only this semantic change analysis, and this task require a large computing facility, right? You should have at least 24 or 48 GB graphics card, and you have at least 8 GB, 8 TB storage, RAM, all things. Then only this take it the task, because here you doing two things and extracting the feature extraction. When you do the feature extraction will happen, take the model, you get no memory exhausted problem, right? And you cannot go for the larger batch size also. So many problems you'll encounter this problem, right? So we were struggling, but somehow we are able to design and develop the model called SFS CDNet 2024. This already available, right? Published. So you can download that. So this task. And so on, others model also will be coming up, you can see that as well. And this is just as a framework, right, how to do that. So here as a training phase and the test phase, right. So in training phase you see the T1 image, T2 image, and then here we have called training sample T1, training sample T2, and then we have getting the deep learning network with the parameters, and then here the loss computation will happen where the ground truth need to given, and then you have called predicting the vanish change map, and then back propagation algorithms which goes to your parameters part here, and then prediction error need to compute, then your finally update the parameter which is over here, right. So this is called training phase here, and then testing phase. So you have to give unseen image T1, test image 1 and 2, and then you get the apply the train model what you have trained, finally you get the bandit change map. Okay, this simple as a framework, right, training framework right now. So now this model is happy to see again came, right, unit model. I'll now quickly will teach you how unit model can be used for the change analysis, right. So this model is not new. So now since we have two input images, right, so we need to create a two encoder. Instead of the single encoder, we need to create the two parallel encoder, that's all, right now. So you can see here input image 1 T1, this one encoder, this other encoder, right, all the encoders coming, and then here after this here last concatenate, and then after that we need to do single decoders only, right. So decoder is not changing, what need to be do modification is only the encoder part, right, so that network should able to accept the two images, right, T1 image and T2 images. You have to give image also, and then later on the ground truth also need to give in that, okay. So this is what the first simple model, what my student did it in that, and all the things are here mentioned, nothing new here. Same model that used for the change analysis right now. Then this is encoder decoder for the change detection analysis, which model design over here. So this model again what we did, previous you see there is no skip connections here, right, without skip connections. Now this is with skip connections. So how is skip connections happening, see here, each layer. So we are getting output here, and then from the previous both need to concatenate that, right. So concatenate and then give it to the decoder sides. Like here from the here this also concatenate and then given that, right. That's called complete unit, right, with the skip connections. This model can also give you the change map, right. But since you went doing research means you have to bring some innovations, some novelty in the model, so that get published in the reputed journal, right, transactions. Then finally what we did it, we thought that we come up different idea. So this is a model encoder, and then we have just subtracted that both features, and then we have design called MSA block, and then this GL gated linear ASPP blocks. Two things we have introduced new things here, right. So these are the novel contributions ours here, and then decoder side here we have not done any changes. Only the changes what the modification did and novel contribution is that bottleneck. Only we have introduced the blocks, right, and this work is given the best result at the time of whatever the benchmark was available at, right. So basically this is nothing, the multi-scale feature block we have. This whatever you see, these are helping for the to accept the multi features from the data. Whatever the difference you have, subtracted the features is there, from that use it. And this is very good methods, right, use that for that. And this paper, as I already told you, this is published in this transaction in 2023, but it was actually available online 2022, but submitted in 2021. So 21 to 23, this took a lot more time for us to get it, get through in this transaction. And this is a block which I told you we introduced. So like I call gated linear ASPP block. First what we introduced that. I'll not go much deeper. You can read the research paper, get more idea. Another is called modified self-attention block. So modified self-attention block is designed over here. These two are the new things, right? What be as a novel contributions in the paper. That's why get published in the transaction labels, okay? And this model which we design is used for the 4 data, tested on the 4 data set. It's not like to the model get for generalizations, right? So these are the 4 data sets. So these data set are like here, air change benchmark data set 1, Onera change direction data set, lever cedar data, WHU building data set. So it's mixed culture, mixed data set, right? Complex data also there. As I told you, this is a complex, right? This is not that much complex. So column 1, column 2, column 3, column 4. Sorry. So these are the 4 the data set image samples and correspond the ground. You can see that over here, right? And quickly I'll move. So this is what the implementation detail of the model which we designed. Loss function, binary cross entropy, optimizer radom, operating system used in that 30-video operating system. So we were able to do 8 GB graphics card with RAM, NVIDIA Cordo 400, and all models was shows convergence for all the data sets with for after 100, right? 100, 150, 50 the epochs, right? Each data set, each are on different data sets. This is just as a research point of view here. So you can see this is the ablation study what model we have designed. So from the without pre-processing, we have also done some pre-processing as, and then intermediate stages. So here you can write green color indicate that what the block is present in these things, and cross means that is removed, and computed all the F1 score, precision recall, kappa, IOU, and OE, right? You can see that final the model which we design is having the better results, right? Like all the data set, right? Data set 1, 2, 3, same things we did it, and then finally these are the feature map visualizations of the proposed model. Ablation study is must. Whenever you design, propose a new model, make sure that you have done ablation study. Ablation study means what is the importance of every blocks, every new module which you have introduced, that the impact of this. Okay, that is very important. So image 1, 2, and then corresponding map, and then here the before this modified self-attention, after this, and after GL ASP block. So you can see that feature extraction is here the improving visually as well, right? So this is a comparison if you see. So all the set of models and F1 score, a precision recall, you see the model which we design is giving the best result on data set 1, and then data set 2 also. The model which we design, F1 score see very good. Kappa coefficient is also very good, IOU. Even this OA is not important here, right? Overall accuracy, right? This is not right parameter, because if you see that also most are the giving very good result, but this also is our model what we design is pretty good, that, right? Then data set 3, you can see the results, data set 4, and 4 data set also result is pretty good compared to the any benchmark what is available in that time. See, that time was benchmark 2021, right now. So that time we compare only 2021 because we submitted 2021 work, right now, during the COVID time, right? So these are the prediction results. So all the benchmark, and this is a model, and this is you can see the grounds, right? So you can see that yes, it's better model, but I would not say that very excellent, right? That time, right? Now some better models available nowadays can be used as well, right? So this, apart from this, we did also the computational complexity analysis, which said parameters, flops, average training time, right? Minimum, and then prediction time per image, which is in milliseconds. So you see that here, the model which we have designed that taking 158 milliseconds, right? Whereas this triple loss model, which is taking 140. And no worry much about this part, because ultimately we are not doing real time, right? It's everything we are analyzing. So little bit time is more prediction, no worry, right? Okay. Medical field you need real time. Data sensors coming and then you need to do image analysis. But for satellites, right, this kind of task like urbanization, other change analysis, monitoring, it is not real time, right? It's over the period only, right? And these are some recent development, right? You can see that already we can help get more learning from there. Yes, this liquid neural network also can be used for the change analysis, right? GIAN models that can be also used with the designing for the new models as well. So if you work on this with available models, you can come up with the better deep learning model for that task, okay? With this, I will stop here, right? Because rest all the things are that already you have seen, but one thing I'll just show you that as well here. So this again change analysis, right, which from my lab, right, that is called bitemporal SAR data, right. So you can see that again the T1 image, T2 and then ground truth and then finally the H last column is our proposed models, right. So for this also we got already published this and also got the best paper awards also. So we are working basically mainly the optical and the SAR, right now for this task. Can be used hyperspectral also. Data is available, few public available. Okay, that's all. Thank you. Any questions? We can take it afterward because professor has to keep the takes. So thank you all. You can do RGB, also you can do multispectral. And if your model is giving the result in both the cases, that's very good, right? Look at the availability of data, right? Multispectral cases, you have to again do the dimension reductions, right? You cannot use all bands. See what are the useful bands? Those bands you can use that for the change analysis. That's not a problem. And if you're doing if you face any problem, you can reach to me, right? We'll help you, not a problem, right? My all course is going to available in GitHub, no worry, right now. So you can follow, you can take the help from there. Okay? Thank you all. Oh, so you will be collecting, no?
I think I will need a couple of minutes break.
No,
so they can rest.
Fine.
It's connected, right?
We have converted, but I don't know if it will work with this or not. For quite a long time it is working.